This section explains the LLava model and code implementation. Let's first look at the LLava model overview. The LLava, Large Language and Vision Assistant model, integrates vision and language processing using a combination of a vision encoder, a language model, and cross-attention mechanisms. Vision encoder extracts visual features from an input image. Language model processes text input and generates predictions. Cross-attention mechanism merges visual and textual features for vision-language understanding. Vision encoder. The vision encoder in LLava is based on ResNet 50, which extracts feature representations from an input image. The last few layers are modified to adapt it for vision language tasks. 1. ResNet-based feature extraction. ResNet 50 processes an input image I and extracts feature maps as follows. 2. Adaptive average pooling. To obtain a compact feature representation, the feature maps are pooled as follows. F-pooled represents a single vector summarizing image features. 3. Feature projection. The extracted features are projected into a common feature space as follows. W1, W2 are projection weights. D is the embedding dimension. G, ELU is a non-linear activation function. Language model, transformer-based text processing. The language model processes text input using an embedding layer and a transformer encoder. 1. Token embeddings. Given an input text sequence T, each token is converted into an embedding as follows. TI is the token index in the vocabulary. WE is the token embedding matrix for vocabulary size V. 2. Positional encodings. Since transformers lack an inherent notion of order, positional encodings are added as follows. PI is a fixed sinusoidal positional encoding as follows. 3. Transformer encoder processing. The token embeddings are passed through a multi-layer transformer encoder. For each transformer layer, multi-head self-attention, QKV are projections of the input embeddings. Feed-forward network. Layer normalization and residual connections. Cross-attention mechanism. Vision-language fusion. The extracted vision feature V needs to interact with the text features H. This is done using a cross-attention mechanism. 1. Query key value projections. We project both textual and visual embeddings into query key value representations as follows. 2. Attention computation. We compute cross-modal attention scores as follows. A represents how much each text token should focus on the image. The fused representation is as follows. The final output embeddings are as follows. Residual connection ensures stability. Text generation. Finally, the language model generates token logits based on the cross-attended features. W outmaps embeddings back to vocabulary logits. The final output probabilities are obtained via softmax as follows, which allows the model to generate text tokens conditioned on the image. Now we implement the LLava code. Language model class. Vision encoder class. cross-attention class. Enhanced tokenizer class. LLava class. Testing the LLava model.